Assalamu alaikum. We will start the second session now. We will start with a paper entitled Blockchain Driven Smart City Review of Key Application and Emerging Trend. Please, the author, go ahead. Kisara, Wimal.
Hello.
Okay, hello.
Hello, very good morning to you.
Good afternoon.
Okay, sorry. So,
You can
hope that you can see me.
I see you now. You
Okay,
are
sorry.
visible.
Okay, sorry about the blurry colors. So it's really too early in Ireland. So I'm
Yeah,
going to share my screen now.
okay.
Uh, okay, I think I cannot share the screen while someone else is sharing. It says.
I can help you if it's possible. Mhm. Now it's working? You can now.
Yes, I can. Okay. So hope that you can see my screen now. Okay.
Large the
Yes. Can you see my presentation? Hello.
I see it. Yes, I see.
Okay. Okay. Good. Okay. So yeah.
You have 20 minutes, 15 minutes your presentation, and 5 minutes for question, please.
Thank you. Thank you very
Okay, go
much.
ahead.
Okay. So this presentation is about blockchain-driven smart cities, and we will be looking at key application and emerging trends. So the paper or the presentation is more toward of current literature. So this is a kind of a narrative literature review. So we have gone through all the available literatures and then found a conclusion. So I myself is the first author along with Gary Cullen and John Donovan. We all three located in Ireland and attached to Atlantic Technological University in Ireland. So I'm the presenter here, Kesar Vima. So let me start my presentation. So this is the presentation flow. I start discussing about smart city, then the blockchain technology, then I go to 6 key component of a smart city, and then I go to each and every component separately. Finally, the future trends, and I will conclude my presentation thereafter. So let's look at what is a smart city, what is the smart city concept is. So this is, so it has a broader explanation what is a smart city and how it works and like that. So this my idea is more toward technological point of view. I'm coming from the computer science engineering background, so I'm giving you more of a technical uh, introduction to the smart city concept. So first of all, we are talking about it is there to enhance the urban living. So smart city concept is about enhance the urban living. So smart cities leverage very advanced and latest technologies to improve the infrastructure, efficiency of it, and quality of life of all the citizens around it. So then we talk about the sustainability and resource optimization. So smart city is there focusing on on optimizing the assets and the natural resources for long-term sustainability. So finally, we talk about data-driven decision making. In smart city, we can see there's a vast uh, number of sensors or Internet of Things devices are connected to each other, creating a broader connectivity and connection, which gives more and more data. So data will be used to make the good decision or enhance decision to enhance and optimize the needs of uh, uh, digital citizens or the citizens within the smart city. So this is a nice diagram or nice picture of a smart city. You can see how each and every component is interconnected. So in my case, it's really mandatory talking about Internet of Things or IoT devices. That's why I have highlighted it. So gives you understanding about the concept of smart city. So everything will be interconnected. So this is a very data heavy infrastructure we are talking about. Each and every device is connected. Here you can see a drone and an autonomous vehicle, a robot, humanoid. So everything is connected here. So next we'll roll back to the blockchain technology. So what is this blockchain technology? So blockchain technology, even though the blockchain technology had it backing way back, however, when Satoshi Nakamoto in 2008 first present its paper towards the Bitcoin or introduced the Bitcoin, this is where the blockchain technology officially come to life, even though the concept was there back days. So in 2008, along with the birth of Bitcoin, the blockchain technology come to the mainstream. So thereafter, mainly it has been using for cryptocurrencies. However, later researchers and scholars realized the blockchain technology has more capabilities and more capacities, more toward different sectors or industries, so that it has been utilized to use in almost all the industries today. So that's how the blockchain technology is about. I'm not going to go deeper about the technological aspects. Rather, I'll be discussing about the characteristics of blockchain technology. So first thing, and very important, it gives a decentralization and the security. So blockchain eliminates the central authority. So when we use the blockchain technology, there won't be a central server or central governance that we have to rely on. It always decentralized. And security is the first thing. So we can see it's ensure secure and tamper-proof transaction. So, and then we have transparency and trust. So all the transactions are recorded in a public ledger, so we can achieve the transparency actually. And then the trust is there, enhancing accountability and reducing the fraud. So finally, we can talk about efficiency and automation. So latest, it comes to a smart contract after Ethereum emerged. So with smart contract, we can do automations, and it also gives the efficiency to deal with blockchain platforms. So what I'm going to do is, this is about a literature review or narrative review. So what in order it for understanding of all the researchers or future researchers or future readers of this paper, what we have done is we have categorized smart city into 6 key components. And thereafter, we have been discussing the blockchain applications and benefits within each of these component of a smart city. We have took 6 categories, and each and every category we will be discussing about how blockchain technology has been affected and will be affected, or how it will be benefited and will benefited in the future as well. So when it comes to categorization of smart cities, there are plenty of researchers and scholars have done really pretty much good of works. So they have been categorized toward different characteristics and dimension and like that. However, this study based on Trincast 2024 publication, and based on this particular paper, we have been shaped up, or we have been arranging our study under a 6 main components or topics, so which are actually the public health service and public safety and security, digital infrastructure and connectivity, urban mobility and transportation, transparency in government and citizen engagement, and finally we have environmental and resource management. So now what I'm going to do is I'm going to take each and every of these component one by one and discuss what are the current application that we have today in when it comes to blockchain technology, blockchain applied applications, and what are the benefits when we apply blockchain into this solution or this application. What are the benefits and what are the challenges that are still remain, which future researchers should address. So under the digital infrastructure and connectivity, we have applications like 6G based smart application, IoT based car pollution monitoring, intelligent learning platform, smart university application, and smart education platforms. By integrating blockchain into this application, we have been benefited like this. So enhanced security has been always there, and transparency and reliability has been achieved. So improved data integrity in IoT systems is another benefit that we have. Fraud prevention in smart education and secure financial transaction. I'll take the secure financial transaction for an example to explain what I'm talking about. So let's take the smart education platform. We all know that if it comes to an education platform, there is always a fee, like transactions are involved. So when student registered with the university, they have to pay the tuition. So then when we integrate blockchain with this kind of a smart education platform, what we can achieve is the security. So blockchain will be handling the transactions. So blockchain is very popular when it comes to handling uh, money or currency. So we integrate blockchain technology with smart education platform to uh, handle all the transactions. So we can have a transparent, decentralized, and very secure platform for dealing with transactions. So likewise, when we integrate blockchain technology into an application of this component, we can have much more benefit. Even though we have much of a benefited, we always have challenges. These are the challenges, these are the things that future researchers should address in order to be or make the blockchain as part of the key component of smart city concept. So in here under this component, digital infrastructure and connectivity, we have challenges such as high implementation cost, integration with legacy system, and scalability in IoT and 6G. So these are the challenges we have. So all of these things I'm discussing about is from already published literature. So this is a narrative review or a literature review. So all of these things are based on already published research, already published work. So then we go next to our second sorry. So we go to our second component, urban mobility and transportation. So we have application like crowd sensing in intelligent transportation system. So dashcam based accident detection systems, authentication for transportation in cyber physical system, vehicular communication, and more importantly, secure data communication in autonomous vehicles. So by applying these things, so by using blockchain technology in this application, we have achieved these benefits such as enhanced security, privacy and interoperability, improved accident detection, data management, and we have efficient vehicular communication, secure and decentralized communication. So still we have challenges such as integration with existing infrastructure, scalability is also a concern here. So I'll quickly move forward. So we have public safety and security as the next component. We have applications such as road safety, crime monitoring and workplace safety, secure data sharing in financial institution. So, and we have achieved again the security and forensic capabilities, very improved forensic capabilities, again, secure and efficient data handling. So we have challenges, high computational overhead, integration with legacy system or currently available system is challenging. Next, we have public health services. So when it comes to application, we have secure sharing of patient record, remote healthcare, and electronic health record management, and cloud-based data handling and data storage. So when we are dealing with patients' data or data in healthcare sector, it is really critical. So no one needs their health records to be exposed. So we will be definitely dealing with blockchain-like technology to enhance the security. So we have benefits such as enhanced patient autonomy, data security, and privacy scalability, like that. So still we have challenges, high cost, large scale implementation is required, and balancing in between private and public cloud, public chains. And environmental and resource management, we have pollution monitoring application of blockchain, and we have water management, agriculture, water rights, and forensic resource management. So we have such application. We have been getting the benefits such as transparency, resource efficiency, and reduced transaction cost. Still, we have challenges such as scalability and high energy consumption when we are dealing with consensus protocols like proof of work. Finally, we have transparency in governance and citizen engagement. We have applications like aid distribution, e-tendering, voting system, and benefits such as improved accountability and secure transactions. Finally, we have challenges such as scalability and voter accessibility issues. So this is about all our 6 categories, 6 components. So next, more importantly, we have been also discussing about future trend. What will be or where will be blockchain will be positioning in the concept of smart city. So when we take the sustainable and governance, so blockchain tackle economical, social, and environmental issues, boosting urban competitiveness, governance, and sustainability. So when the smart city, when we are making the smart cities a sustainable and governance, so we are going to apply blockchain in future. So security and efficiency in IoT and supply chain. So we can expect blockchain to be there in every supply chain because it gives the transparency, traceability, and also reduce much of the errors. So when it comes to IoT, when it comes to supply chain, we can expect blockchain will be always there. So future innovation and business application, again, what will be the business application? Like we can have some solution like lightweight IoT protocol, again, towards IoT, and decentralized security. This is very important. We are not talking about centralized point of a security, not that being governed by a centralized server. No, the security will be decentralized. Everyone has the distributed, decentralized layer of security in smart city concept. Finally, I'm talking about the healthcare, not only healthcare, but everything. The data governance is important. However, when it comes to health records, we keep those things are very crucial in terms of security. So in the healthcare sector, we will be having blockchain in the future that will be govern all the records in healthcare. So I would like to conclude my presentation, conclude my future trend chapter, saying that definitely in the future, the blockchain technology will play a crucial role in each and every smart city, or blockchain will be backed smart city concept as a very advanced and very good technology in terms of security. So this is the conclusion, or briefly go through what my paper is about, what our paper is about. The paper is more about overview of blockchain transformative role in smart city and analyzing integration of it across 6 key components of smart city paradigm. Then more importantly, we have been discussing about future direction and what are the future things have been done in terms of what proposed by the current researchers. So all these work are based on past literature. So this is a literature review. So I have added some of the references. This is not all. So I have added some of the main references. It has to be plenty. So my paper covers everything. So these are the references. And I would like to acknowledge that the research is funding by aligned with Atlantic Technological University. The funding is coming from, actually co-financed by Government of Ireland and the European Union. So I would like to thank them for their funding and the opportunity. And finally, I conclude my presentation. Thank you very much, and would like to get...
Thank you, Mr. Ashkar Akash, and thank you for your presentation and challenge of different surface of smart cities. Is there any question for the author from the attendee? Is there any question? Okay, Mr. Ashkar, I have one question to you really. Do you know that blockchain, it's a distributed ledger accessing the data in transparent way, but there is a limitation on the number of block which we can mine using blockchain. And as you know, smart cities, especially with the big data, need something which can contain all huge amount of data. Is blockchain the ideal candidate for that?
Yeah, so most of the challenges have been identified this scalability issue. Yes, I accept your concern. Yes, there's a scalability issue when it comes to big data, big lot of amount of data. It will be really challenging for blockchain to adapt. However, so the very first or the Bitcoin's own consensus protocol proof of work is having this lacking of the scalability issue. So now it is going towards a positive way. However, after a period of time in last 5 years, there have been introducing plenty of new consensus mechanisms. So these consensus mechanism is not having the scalability issues. So I accept it when it comes to storing all the data within a one computer in order to build a peer-to-peer network. It's really heavy amount of data. Dealing with big data is not possible to do it. So that's why you can see most of the places the scalability issues has been mentioned. So however, the researchers are working towards to solve this issue by introducing different consensus mechanism, and we are going toward a very positive way. So we have been passing this compass this proof of work consensus mechanism. Now we are dealing with proof of stake or delegated proof of stake and so on. So this way we will be definitely in near future achieve this scalability issue, how we deal with a big amount of data or big data. So for the moment we are still researching. However, in very near future, there will be a definite solution. After this solution, it can be applicable to almost any scenario. So that I can be certain about. Yeah.
Okay, thank you very much. Now we will go to second paper in this session, predictive modeling of battery second life performance using support vector regression and voltage feature. Go ahead to the author, Madam Ismail Hussein. Oh.
Assalamu alaikum. Am I audible?
I see your presentation. Salam alaikum barakatuh. I see your presentation. Go ahead. You have 15 minutes to present your work and 5 minutes for question, please.
Good morning, everyone. I'm MD Ashikur Rahman Akash. It is my pleasure to present our research on the predictive modeling of battery second life performance using support vector regression and voltage feature. This study aims to address a crucial challenge in the sustainable resource of lithium-ion batteries, accurate and cost-effective state of health innovation. The here here are our presentation outlines, and we will go through this topic in like a background, objectives, introduction, literature review, research contribution, methodology, experimental dataset, and future expectation, modeling, development, performance analysis, and vision, conclusion, and the references. The background. Lithium-ion batteries are widely used in electrical vehicles and energy storage systems, but they are degraded over time. Once their capacity falls below the 80%, they are retired from high performance application. However, instead of disposal, these batteries can be repurposed for second life applications such as the great storage and backup power. A crucial challenge in this process is estimating of the SOH of these batteries are really time working in the using the support of vector regression to estimate it SOH based on minimal voltage based features and make in a cost-effective and scalable solution. The objectives of our studies are that to develop an efficient and accurate methodology for
Your voice is muted.
hello,
Hello?
sir,
Your
am I
voice.
audible?
I hear you now, but voice stop for 1 second. Yeah, go ahead.
The main objectives of our studies are to develop an efficient and accurate methodology for SOH estimation in the second life lithium-ion batteries. To use support vector regression to predict SOH based um, to key voltage based the health indicators, the time interval time interval equal charging and discharging voltage difference. To train the supportive voltage regression model using the fast life battery data and validation it using necessarily lithium-ion battery gaining dataset. To access the model accuracy using the root mean square error and the mean absolute error. And the last one is to provide the mm, low cost to provide a scalable solution for real-time SOH estimation that does not require any expensive monitoring the infrastructure. The 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 problem is to statement. As battery degrades estimation, their health become a challenge, and especially in second life application, where the traditional monitoring systems are available existing, the SOH estimation model are rely on the complex electromechanical simulation or require large data set, making them the computational expensive. A simpler and more particular solution is indeed one on the leverage machine learning with a minimal input feature with minimal accuracy. This is where our proposed for a supportive vector regression model come in, offering a lightweight while effective alternative. Research gap. Despite of number of studies on SOH estimation using the machine learning, gaps remains mm, there. The many models focusing on only the first life of batteries and lack validation in the second life application. Few studies explore the time-based health indicators like uh, time interval equal charge and discharge and voltage difference. The large level dataset are the often required, which are not always available in the second life scenarios. The limited research has been done on using in supportive vector regression for second life battery SOEs. Our study addressed these gaps are proposing an SVR model that uses the minimum voltage based features for the accurate and scalable HOH estimation. Literature reviews. Previous research has explored various machine learning techniques for SOH estimation, including in neural network, XGBoost, and gradient boosting, which have showed high accuracy with the reduction dataset. The generative adversarial network gains for the data accumulation to improve limited level gaining data. The hybrid model is combining the evaluation circuit model with the broadband impedance measurement. Then the adaptive neural fragile impedance systems models for reducing the emission error and the training time. The Bayesian optimization applied for or SVR, the support vector regression, enhancing model the robustness under the different cycling conditions. Our study builds on these findings and contributes by validating an SVR model for second life batteries application. research contribution. The key contribution of our study includes the development of an SV model trained on the fast battery life data and applied second life application. The introduction to voltage-based health induction, the time TIECV and the TI-DVD for state of health estimation. The application of our model to NASA's battery gaining dataset for validation, achieving the high predictive accuracy with low MRS error and values across the different batteries dataset, providing practical low cost and real-time solution for the second life battery application, extending in battery lifespan for reducing the electronic waste. Our methodology aligns with the circular economy approach to batteries lifespan management. Once retired the high performance application on battery as available for SOAs. This with acceptable SOAs are repurposed to second life application. While those features are degeneration and directly recycling, this approach maximizes our efficiency in the environment impact. The methodology. In the battery state of health, we see here the equation we use for the SOH by CI divided by CO. The CI is the cycle of the capacity cycle, and the CO is the rated capacity. The supportive vector regression is the support vector regression in the supportive learning language algorithm that effectively model nonlinear relationship, making the ideal for SOH estimation as batteries. The proposed workflow for our project, our work is the proposed estimation method includes the loading the necessary data batteries, gaining the dataset, extracting the key health indicators and the voltage measurements, the training and SBR model on the fast life dataset for first 1,000 cycles. Applying the trend model to second life battery cycle to estimate the SOH. The evaluation of model performance using the RMS error and the mean absolute error. This process enables our accurate SOH estimation with the minimal data input. Second, the experiential dataset acquisition. We use a NASA's battery gaining the dataset, which is data from the lithium-ion battery, the B00P0005 voltage during the discharge and charge in this figure. We use the 2.2 ampere hour capacity of a battery to the key of the feature expression for the voltage measurements. In the figure, figure 4 illustrates the TIECD and the TIE-DVD curves displays the comparative decreasing trends as a cycle member increase rememorizing and battery SOH behavior. This constants the declines and coupled with our vector inductor. In here we maintain the voltage level 3.5 to 4.5 volts, and the specific result we show in there is 3.8 volts to 3.6 is voltage. In the model development, we here use the B005 minimal over the function estimation minimal objective against the number of function evaluation internally the sharp of the objectives. Figure number 6 shows the minimal object versus function and evaluation for the battery 006. The performance analysis is on our evaluation is MRS and the MEA variation of our model. Our model is trained using a first life cycle and validation the second life data. The key step of this using for steps using the SBR in the Gaussian kernel to capture the nonlinear relationship and the optimizing model parameter using the Bison's optimization. Performing across the validation to prevent the over limiting optimization. Performing across the validation to perform overlifting the steps. In the battery of 007, we saw the actual and the estimated SOH level. Here is our comparison chart for RMSE and the ME of for the SOH estimation across the battery. Here is our SOH estimation on RMS error and the mean absolute error difference of the batteries. For the batteries, we can see the B0075 is RMS value is 0.0061 and the mean absolute error is 0.0047. For the battery 0006, we can see the RMS error is 0.001. 158 and the mean absolute error is 0.00126. For the battery B0007, the RMS error is 0.0047 and the mean absolute error is 0.0038. Overall, we can see that as the model performs best for the battery B0007 and the worst for the battery in B0006. In conclusion, we can say we develop an SBM model using that time interval equal charging and discharging in voltage difference for the real-time SOH estimation. The model was trained for the first life battery data and validation on second life data using necessary battery gaining datasheet. Our approaches achieved high accuracy with low road RMS values, and this method is offered a sustainable low-cost solution for second life battery health monitoring. The future research can incorporate additional factors like temperature validation to further improve the prediction accuracy. Here the key reference for our presentation. More reference are in our paper we included there. Thank you, everyone.
Thank you, Dr. Ashkar, for your presentation. Is there any question from the attendee? Can you return to figure number 9, Mr. Ashkar? Can you go? Yeah, that's very good. Here's something strange to me, really. Why SOH, state of health, increasing with the time after decreasing? For example, after 10 cycle, the state of health increased. Why? Do you hear me, Mr. Ashkar?
Yes, I'm hearing you.
Yeah. What is the reason? What is the reason for that? State of health normally should go down with the time. Why it's go up again after decreasing, then go up, decreasing, go up, and so on?
the captured battery resolution exhibits the best alignment between the actual and estimation of state of health with the minimal deviation across the cycle range. In it which the model's high accuracy for this battery.
يعني is the state of health can be better after a number of cycle of charging discharging?
Yes,
How is that? Very strange for me really. يعني the state of health for the battery after decline to 0.76 after that it's increased to 0.77.
because of the temperature issues, the external pressure maybe, and the equilibration issues.
Okay. Could you also go to the figure before the figure 9? Cycle number? No. This is this is charging and this is charging. The curve of charging, this is charging. Yes, this one. You mentioned here time on the horizontal and the voltage on the vertical. And look to me that this charging depend only on time. Is it true or should be on time and the load itself?
Yes, it's on the time.
يعني it should be the load must be a function in the curve or what?
It's the voltage charging and discharging in during the voltage versus time layout.
Okay, thank you very much, Mr. Akkar. Thank you, Mr. Ashkar. Now we will go to the next paper entitled Optimize the hardware implementation of FOC for BLDC in UAV using 2DOF by blended by and IB controller and using BSO, I guess. It's okay, go, Dr. Abdel Hadi. Just a moment, I will let it work. Just a moment, I will let it.
vehicles using a 2-degree of freedom controller tuned by vertical swarm optimization method. And this work is a collaboration with my colleagues, Mr. Gary Gaya and Professor Stephen Liu from the Institute of Control Systems at University of Kaiserslautern, Landau, Germany. Let's start with the motivation and why this research is, or this work is important. Actually, the unmanned aerial vehicles are widely used in many industries and applications such agriculture, delivery and surveillance and disaster response, inspections, filming, and military and others. And as we can see here in the right-hand side, we have the figure of the quadcopter, which is the most popular unmanned aerial vehicle application. And as we can see that there are 4 motors or propellers which they generate the thrust that can hover the drone and move the drone on roll and pitch and yaw angles. So that's why we can say the precise motor control and stability and accuracy of motor control lead to stability and accuracy of quadcopter or UAV itself. And the challenge of this work, we have many challenges. However, we are focusing on 2 or 3 challenges. Let's start with the first one, which is the drifting issues under disturbance. Actually, because as we know, unmanned aerial vehicles usually or in many cases they are used in outdoor applications. And so the wind will be the most affected disturbance in this case. And the second challenge here, we have the parameter uncertainties of the motor, and the control tuning could be more complex and difficult to design the control or the controller with the parameters uncertainties of the motor. And the contribution of you need to click into. And the contribution of this work, which is related to the main challenges, and to overcome these challenges, actually, for first one, the disturbance issue, we utilize a 2-degree of freedom BI controller, which can make the bandwidth of the system larger and add or give more degree of freedom to the system, which can handle the disturbance and reject the disturbance as well. And for the second challenge or problem statement, which is parameter uncertainties of the motor and the complexity and difficulty of mathematical tuning and design of the controller. Instead of that, we propose that we can use an artificial intelligence optimization technique, which is vertical swarm optimization method, to do or to overcome uncertainties of the motor parameters and the complexity and difficulty of the control design. Let's move to the BLDC model, which is the model of the motors that we are using in our drone. Actually, the BLDCs are mostly used in or widely used in many UAV applications, unmanned aerial vehicles applications, because the high efficiency and the torque that can provide compared to other motors. And on the left-hand side, we have the mathematical model of the BLDC, and on the right-hand side in the table, we have the parameters of the internal resistance and inductance and motor inertia and so on of the BLDC itself. And here we have the hardware setup. Actually, the hardware setup, we have two motors. The motor on the right-hand side, which is the tested motor, where we have implemented all control strategies that we'll explain later. And on the left-hand side, we have the wind disturbance motor, because we just want to use our tested motor under disturbance. That's why we use the other motor to generate high wind or fast speed wind to simulate the real-time application in outdoor. And here we come to the control strategies. Actually, we developed four, or we implemented four control strategies. First one, which is the open loop, and then closed loop, and then field-oriented control, which is the most advanced techniques used in many industries and applications. However, we proposed our new optimized field-oriented control, which using 2-degree of freedom controller and tuned by particle swarm optimization. It's nothing, just extension of field-oriented control. And let's start with the open loop. Open loop is nothing, just we have the BLDC and the electronic speed controller and microcontroller and the battery, of course. The electronic speed controller is such a three-phase inverter. And in microcontroller, to do this structure in real time, actually we have to apply the voltage for the motor, and we have to test or measure the actual speed. And based on this applied voltage and measured speed, we need to see how is the relation. And by using this relation, we can apply the set point or desired reference speed that we want the motor to follow. Then going to closed loop, which is nothing, just open loop plus feedback. And here in this feedback, we use magnetic encoder for measuring the real reference speed of the motors. And actually, the magnetic encoder is just measuring the angle of the shaft of the motor. Then by using the derivation of that on our software, we can calculate the speed of the motor, and it's just closed loop. And we use a BI controller, and we tuned it by Ziegler-Nichols method, which is the most basic one. Yeah, Ziegler-Nichols method, which is one of the most common methods are using to tune the BI controller. And then we come to field-oriented control. As we mentioned before, it's the most advanced techniques used in many manufacturers and industries. However, it's considered an expensive method, because we have to use different sensors for current sensors. As we can see here in the structure, we have IA, IB, which are the real current measurements from the motor, which is a little bit expensive than normal. And we have to use computing and high power microcontroller or microprocessor for this method. It's basically just this field-oriented control to transfer three-phase system to DQ reference frame, and to control only. And by that, we have two control loops. Inner control loop, which is the current control loop, and it operates at 10 kilohertz, and tuned the two BI controllers in inner control loop or current control loop, tuned by magnitude optimum tuning method. And for the outer control loop, which is the speed control loop, it operates at 1 kilohertz, and tune the BI controller of this method, of this loop, tuned by symmetry optimum tuning method. And yeah. Finally, we move to our optimized or proposed optimized method which just FOC. However, instead of using normal BI controller here, we use 2 degree of freedom BI. And as we mentioned before, we use this one to add more degrees of freedom to the system and to make the bandwidth of the system larger, which can handle the disturbance more than normal BI controller in this case. And by this, when we use this blended or 2 degree of freedom controller, that means we have more degree of freedom. And even from the structure, we can see that the system will be mathematically more complex to be and difficult to be tuned by mathematical methods. So we used particle swarm optimization method, which is artificial intelligence method to do this tuning instead of doing by human. And particle swarm optimization method is nothing just like it's just artificial intelligence trying to search about the best gains of some boundary that we have to set from the beginning to find the best gains they can give or make the system to give the minimum error and to compare many different gains and searching about the best gains. That's everything about particle swarm optimization, and the flowchart of it is presented here. Yes, and we do this optimization because, as we mentioned, we need to tune the BI controllers of current control loop and closed control loop, and to achieving minimum error of the system. However, we have one problem or challenge that if we use particle swarm optimization or any optimization technique, that means we cannot guarantee how is the shape or the response of the system if we don't use the correct cost function. That's why if we use, let's say, integral square error cost function or integral absolute error cost function, we can achieve minimum response, minimum error of the system, but with some overshoot. And here in this application, because it's quadcopter or drone, we don't have, or we don't like to have any overshoot, that because that could lead to some... Hello? Hello? Yeah, because that can lead to some overshoot, which leads to have some instability of the UAV. Then we use this asymmetric cost function, which just doing nothing, just to weight the negative errors, which are the errors after when the response over the desired speed, and weights that in higher weighting function. And coming to the result, starting with open loop, as we see here, we have in two cases reference tracking and under disturbance. For reference tracking in open loop, it's actually it follows the reference, but as we can see, it's very slow and not very accurate. And under disturbance, cannot handle or reject any disturbance because it's nothing, just feed forward control. So of course cannot handle any disturbance. And coming to closed loop, which shows a little bit similar to the open loop in reference tracking problem, but in under disturbance, actually it could handle and reject the disturbance. It takes a little bit long time, about 3 seconds, but it can reject the disturbance. And coming to field-oriented control, it looks very nice. Actually, we have very nice for reference tracking problem where the settling time, rise time, and the steady state error are very small, so it's perfect for reference tracking. And under disturbance, actually, we have very small disturbance or notable disturbance here. However, that's for this disturbance, that's why we thought about to optimize the method to overcome or reject this disturbance. And we come to the result of our optimized technique. We can see that for reference tracking, it shows very nice result, and for under disturbance case, we have no notable disturbance here, which is the required of our application. And to do some comparison between all control strategies, open loop, closed loop, for reference tracking, they can follow the reference. However, it takes long time and they are not very accurate. And for field-oriented control, it takes about 80 milliseconds for settling time, which is considered very nice. However, in our proposed optimized technique, we achieve 38 milliseconds, which is about 2 times better than normal FOC. And under disturbance rejection, as we mentioned before, open loop cannot handle any disturbance because it's just feed forward, and closed loop can handle. However, it takes about 3 seconds to handle that or to reject the disturbance, which is very long in area in applications such drones and so on. But in field-oriented control, the rejection of the disturbance takes about 1 second, which is considered a little bit long. And our optimized method, actually, there is no notable disturbance. That's what we are looking for to achieve. And to conclude that, we can say that we implement in real time different control strategies, open loop, closed loop, and field-oriented control. And we test all of them compared to our optimized or proposed optimized method. And our optimized method shows much better result than all the other conventional methods, even advanced method like field-oriented control. And we in our proposed control strategy, we just use field-oriented control with 2 degrees of freedom BI controller, and tuning these controllers by particle swarm optimization method. And the future work of our work, actually, first point that we will extend this work to do some online tuning of particle swarm optimization method instead of doing it offline. And to implement this motors or motor control strategy in real-time UAV or drone application, and to do some comparison between when we use our optimization method for real-time drone compared to the other motor control strategies when they are implemented in real-time UAV or unmanned aerial vehicles. Thank you so much.
Thank you, Dr. Abdelhadi. I guess your work can improve. Driving of drone will be much better than before, I guess. In all cases, it's known that control can be open loop. Open loop, it's not.
Yeah, it's feed forward.
It's open.
Yeah, but it's
Okay.
It's feed forward control because
Feedback control, because normally we notice a change or turbulence in the output. So correct the input in order to adjust the output.
Yes.
It's okay.
Yes.
And the type, is it feedback which you shown in your presentation, discrete or continuous signal?
Of course, discrete.
Discrete, not of course, because there is a continuous as well.
No, but if you mean continuous, that means you are
Traditional control is a continuous signal.
No, what I mean here, because I'm working on real-time application.
Yeah.
I implemented this work in real time, in real application. So there is no continuous sign. It must be discrete because there is no microcontroller or microprocessor around
Yeah,
the world.
because you are using a microprocessor, you can digitize the analog signal in order to get sample from it.
Yeah, yes, the point is in simulation, we have two choices that either we use discrete time or continuous time system.
Yeah,
But
but
in real time
yes,
application,
but even Dr. Abdelhadi, even in real time, we can have, but we don't introduce the processor in the system by this way. We make comparator, something like that,
yeah,
in
but
order to compare to
yeah,
signal
yeah,
and get the
yeah, I got you.
differences.
Yeah, I got you. Actually, I have one of the labs which I'm
Yeah, it's called analog control.
yeah, it's analog control, but
Huh?
it's very
Old one.
slow and cannot handle even work.
Yeah, but because you are talked about the frequency of feedback 1 kilo and 2 kilo, so
Yeah.
I
Yeah,
from this
yeah.
point I expect that
Yes.
it's a discrete sampling.
Yeah, it's discrete time because actually here we really in these methods, as you can see, that we really use very advanced techniques such
Yeah.
field-oriented control and our proposed optimized field-oriented control, which really need high power microcontrollers or microprocessors. And what I use from STM microcontroller, actually, it's about 400 mega hertz, which
Yeah.
is very high and very good
Yeah.
microcontroller.
Resolution,
Yes.
high resolution.
Yes.
طيب, if any wind drift happen for the drone,
Yes.
return to the steady state quickly, or you say it's how
Yeah,
many
actually-
milliseconds, something like
Yes,
that.
actually, that was the really the point that which I am or we are working on.
Yeah.
If you can see when we use open loop, the disturbance doesn't reject. In
Yeah.
closed loop, it's
Reject.
rejected,
We
but
resist.
with long
We
time.
resist, but not
Yes,
perfect.
and FOC rejected in small time, about 1 second. However, 1 second in quadcopter or in drones is not small time.
Yeah.
It's considered long time actually.
Yeah.
Yeah, if you go to comparison.
Here, and I have a question really.
Sorry, this one actually 1 second.
Yeah.
It's not small time for
Yes.
aerial applications.
Yeah. Yeah.
You know, it's long time considered. That's why we must
Yeah, it's
think about something.
This
to-
is almost the same as a reference. Yeah.
yeah, that's
Yeah,
without-
perfect. But I'm surprised how you reach the speed from 0 to 300 RPM in no time.
No,
Where yeah, 3,000, yeah, in almost zero time or what?
What?
Almost zero time. Yeah, that change happened in zero time. It's very small, يعني.
yeah, 30
Milliseconds, trivial. Do you know 30 millisecond, it mean,
0.02
yeah.
second. Yeah, that's why.
But where is the inertia of the motor itself? Because the motor has a mass
Yeah,
and the inertia, and when you move something with a mass, it takes more time.
Yeah.
I'm here, how is the ideal case
Yeah.
come like this?
yeah, that's very good question actually, because that's why I told you that we must use very high microprocessors and advanced techniques. If you can see here in inner control loop, we operate the system at 10 kilohertz. You know, 10
To get
kilohertz.
high
that
resolution,
means-
yeah. Better
that means
resolution.
10 kilohertz, that means 0.1 millisecond. That means every 0.1 millisecond we have to create.
Take sample from the output
Yeah.
to the input. Yes.
That means every 0.1 millisecond, we have to see how is the measurement and make a decision about next step every 0.1 millisecond. So after 38 milliseconds, which means about 380 decisions taken, then we can say we achieved to the reference, which is
Okay.
actually really could be.
Thank you very much, Dr. Abdelhadi, and welcome to Saudi. And you have to, I hope to enjoy your staying here, inshallah. Okay, thank you. Thank you. Now we go to the last paper in this session, Secure Pilgrim بالجريمز assistant system using an augmented reality. دكتور أمنة السلمي. اوكي. هو أروى مين اللي هي عمار أمنة فين؟ انت هتعملي اونلاين؟ مين الستودنت؟ لا مفيش زي nobody اونلاين ولا رغب ولا عمار. باي ذا واي the supervisor of the author here, Dr. Amna, but the author, somebody, the presenter is somebody else. رغد, can you share screen from your side please? But I see it here. How is بص هي ظاهرة عندي على ممكن تساعديني يا هي ظاهرة عندي هنا بس نسأل اسمه ايه ده؟ ها؟ لا هي لا موجودة. لا موجودة. انا عارف يعني نستوب شيرنج فايد. تمام انا نستوب شيرنج الاول. اوكي شير. the host isn't okay. share again. طيب انا هنستوب هير. دي كده هنا ده نستوب شير دي الاول. edit. أهو. رغد اهي، انا عاملها here it's host. انا عامل رغد host، مش عارف ليه ظاهرة دي دلوقتي. طيب نوقف دي خالص اهو، وقف لي دي خالص، اقف كده. اوكي، ده تاني. اوكي تمام. It's okay, go ahead رغد. You hear me? قول لها unmute your telephone microphone.
Not there?
لا ده رغد second one.
He wants to share it.
This is a presentation.
Okay, what's happening?
This, I don't know, sound is not coming.
He's muted.
Yeah, but we can control it from here.
No, he have to learn with himself. Yeah. Like he's the host also.
Yeah.
Or we can do like this.
No, no, no.
No, reclaim the host and I will unmute.
طيب ماشي اوكي. وبعدين بتفتحها host again.
No, it's slides out there, don't do that. I'm just
الو رغد.
maybe. So you have the mic? You should rejoin it, okay. Go out and rejoin it. Because maybe like the driver will take time to upgrade it on the phone.
Could you ask the Dr. Abdel Hadi, the one who was here? implemented by your student already. It's okay. What are about the satisfaction of the stakeholder of this project? Mm. Feedback. Yeah. Okay. Best wishes for you and your student, and thank you. Thank you. Oh, no problem. No problem. No problem. Now we want to end the second session. Thank you for the attendee and good luck. Assalamu alaikum.